We spent last week talking about constant velocity, and we spent last week talking about position versus time graphs, which boiled down to, for the most part, at least the examples that we did, constant velocity. Today we're going to start talking about acceleration. And we know acceleration is not constant velocity. Acceleration is speeding up or slowing down. Specifically, acceleration is the rate at which something speeds up or slows down. The rate of change of velocity. Now, velocity was defined as the rate of change of position. Anything that is a rate has what on the bottom of that equation? The rate of change of position was velocity, and it had what on the bottom of the equation? Time. The rate of change of velocity is also going to have time on the bottom. What's it going to have on the top? Not displacement. That would be velocity then. The rate of change of position, or the displacement over the time, would be velocity. The acceleration is the rate of change of velocity. So it's going to be delta V over delta T, the change in velocity over the change in time. That's the main equation, although we saw real briefly on Friday there's a number of other equations that we can use as well. That's the first one, though, the first one that we use for acceleration. It's the one that boils down to the definition of acceleration. The units, I gave you a few different forms of the units on Friday, but in the end, there's really only one that we're going to use. What was it? Yep. Good. Meters per second squared. We could say meters per second. We could say ms to the minus 2, right? But meters per second squared is usually, it's always the form, in fact, that we use. And then we saw this whole big list of other equations that are valid for acceleration as well. We called them our group B equations. In no particular order, we said D is equal to VIT plus 1/2 AT squared. What did VI stand for? Initial velocity. What did A stand for? Acceleration. What did T stand for? Time. Delta D stands for? Sorry? Delta D? No. Delta T stands for change in time, you're right. Delta D stands for displacement, good. Everything in there is a vector except for time, of course, right? No direction associated with that. Now, there's another one that looks almost the same as that. You got to be really careful on these, actually. D is equal to VFT minus 1/2 AT squared. VF stands for final velocity, good. Here's another one. VF squared is equal to VI squared plus 2AD. What does VI stand for there? Initial, no, not initial velocity. Somebody said it back here. Julia? Initial speed? Yeah, it's initial speed, good. And final speed. What does A stand for? Acceleration, and delta D stands for displacement, of course. So you got to be careful here. These are vectors, just like most of the variables are in the first two equations, but these two are scalars, and that's going to make a difference sometimes. You're going to see when that arises. Finally, we have one more. Delta D is equal to VI plus VF over 2 times T. And this one's a little bit different because it doesn't even have the term acceleration in there. We use it when we have acceleration, when something is speeding up or slowing down. We just don't know the value of that acceleration, how quickly it's speeding up or slowing down. All of these equations that are circled in blue here, this one and then the last four, are what we call our group B equations. They are valid whenever we have an acceleration, okay, whether it's speeding up or slowing down, whether we know the value of the acceleration, whether we're trying to find the value of the acceleration, or whether we don't know anything about the acceleration other than it's accelerating. These group B equations are all valid in that situation. We have one group A equation. We've already used that lots. My group A equation, of course, is valid when we have a constant velocity or constant speed. V is equal to delta D over delta T. We said on Friday that now every time we see a problem, what we have to do is ask ourselves a question. before we write down our givens. Okay, we get in that habit of writing down the givens first, and that's important to write down the givens. I'm not discounting that at all. I'm not saying, no, don't do that anymore. That's not important. It's very important to write down the givens. But what we want to do now is something before the givens, and that is to just give some thought to the question. Understand what's going on in the question before we write down our givens. The danger of writing down your givens first when we've got now 6 equations at our disposal is that we get tunnel vision. We write down our givens, we get tunnel vision, we look for an equation right away that fits the givens. And sometimes, if you haven't recognized what the concept is, group A or group B, sometimes that's going to lead you down the wrong path. Okay, so understand the question. Is it a group A problem or is it a group B problem? Is it constant velocity? Is it acceleration? And then write down the givens and see which equation seems to fit. All right? All right, here's a question. It's on page 47. This one says, a hybrid car with an initial velocity of 10 meters per second. It's a good thing they tell us it's a hybrid car, eh? Because if this was not a hybrid car, it would change nothing. A hybrid car with an initial velocity of 10 meters per second accelerates at 3 meters per second squared to the east. How long will it take the car to acquire a final velocity of 25 meters per second? Remember what we said. Temptation is to write down those givens first. And those givens are important. But what we want to do now first is just give some thought to the question. Understand what's happening in the question. And then write down the givens here. What is happening in this question? We're going to get a constant velocity, or are we accelerating, speeding up or slowing down? Kelly? It's accelerating. So what kind of a question is this going to be? Is it a group A problem or is it a group B problem? We said it? It's a group B problem, right? Now that we know it's accelerating, it's a group B problem, we know which equations are valid, those blue ones on the last page. Now let's write down our givens and see if we can figure out which of these blue ones fits the givens here. All right, what do we have given to us? Something is, let's make east positive, something is 10 meters per second. What is that? Is that A? Is that V? Is that VI? Is that VF? Is that delta D? It's VI, good. The initial velocity is 10 meters per second to the east. Good. Something is 3 meters per second to the east. Sorry, 3 meters per second squared to the east. What's that? Chris? Yeah, that's going to be acceleration. We're going to say that's A with the vector R. It's east, so it's positive as well. How long will it take the car to acquire a final velocity of 25 meters per second to the east? Okay, let's write that one down. What's that going to be? Zach, what variable is that one here? Good. VF, 25 meters per second. And finally, what are we looking for here? What's my unknown in this question here? Yes, sir? It's going to be delta T, the time interval here. All right. So VI, A, VF, and T. Remember, we're only looking at those blue equations here because it's a group B problem. It's those equations that you have circled on your data sheet separately from V equals delta D over delta T. Which one do you want to try? Now, before you make a decision, let me tell you that although there's 5 equations squared off in blue there, and probably one of them is the best choice, you can choose whichever one you want without fear of going wrong. If you pick V equals delta D over delta T, our group A equation, our red one, you're going to get the wrong answer because that's not a valid equation. But if you pick an equation from the list of blue ones, the worst that's going to happen is you're not going to get an answer because you have 2 or 3 or 4 unknowns. Okay? But at least you're going to know it, right? You're going to go through it and you're going to say, oh, I got 2 unknowns, I can't solve this. All right, pick another equation. Oh, that one, same deal. I got 2 unknowns in that one too. Pick another equation. As long as you pick a blue equation here, you can, and use it properly, you can't get the wrong answer. You may not get an answer, but you can't get the wrong answer. So there's no fear here. If you're not sure which one to try first, just pick one. Go with it. If it doesn't work, pick another one. If it doesn't work, pick another one. You can't go wrong. Okay, which one do you think works here? We've got VI, we've got VF, we've got A, we're looking for T. Which one do you want to try? Kessler? VF squared is equal to VI squared plus 2AD. All right, let's give that a try. How many people, by the way, would have chosen that one? Okay, interesting. Nobody else. I wouldn't have picked that one either, actually, but that's okay, because there's often, Kessler, more than one option, and even if there isn't, and I say the worst that's going to happen is we're going to have too many unknowns. We try again. So let's start with that one. Let's go with that one. VF squared is equal to VI squared plus 2AD. All right. VF, we have. VI, we have. A, we have. We can solve for D here. Okay. We can solve for D here, although that's not what we're looking for. That's okay. It's not wrong to get D, is it? Okay. Although it's a little bit ugly to rearrange that, isn't it? We're going to go through it this way. This is not the most efficient way to solve this question, but we're going to go through it this way anyways, and then we'll go back and solve it the other way using the equation that I would have used here. All right. Solving for delta D here. Listen carefully to the rules of rearranging. I mean, we've rearranged a pretty simple equation, right? V equals delta D over delta T. And some of you learned to do it probably in grade 8 or grade 9 using the triangle, using that stupid triangle. I told you, don't ever use that again. Because when you get to an equation like this, it doesn't work. Not even close. Listen carefully. What you want to do first is get rid of what is not attached to the variable you're solving for. Okay, get rid of what's not attached. And you do it by doing the opposite to it. Okay, so tell me what is not attached. Tell me what is attached to the D right now. Solving for D, what is attached to it? What variable is attached? The 2 and the A are attached. Don't get rid of those first. Okay, get rid of what's not attached. Mallory, what's not attached? VI squared. So let's take the VI squared over to the other side first because it's not attached. Get rid of what's not attached first. Mallory, how am I going to do that? It's plus VI squared plus 2AD. I'm going to take it over by subtracting. If it was VI squared times D, I'd take it over by dividing, right? VS squared minus VI squared equals 2 times A times D. You guys with me on that? Really what I'm doing is subtracting VI squared from both sides, right? But VI squared minus VI squared is nothing on the right side. Get rid of what's not attached. Then get rid of what is attached. What's attached? Now, I already told me it was the 2 and the A. I can take those over separately or together. Divide both sides by 2A, and look what happens. I'm left with VF squared minus VI squared over 2A equals delta D. All right, it's going to give me delta D. Not what I'm looking for, but that's okay. It's not wrong. The only way it would be wrong is if I solve for T here and it got the wrong number. VF squared, 25 squared minus 10 squared over 2 times 3. 625 minus 100. 100 divided by 6. 525 divided by 6 is 87.5 meters. All right, not what I'm looking for, but now I can turn around, Kessler, and use another equation to find delta T, right? Which one do you want to try now? Okay. VI plus VF over 2 times T. We're looking for T here, right? Hey, get rid of what's not attached to the T. What's not attached to the T? It's all attached to the T because it's inside brackets, right? So let's get rid of what is attached to the T. Watch this. This is kind of weird, actually. Let's divide both sides by. We can do this, right? It's all in brackets. It's kind of confusing, though. Make sense what I just did? Julian? Let's say we had D is equal to X times T. Could I divide both sides by x? The x's would cancel, right? That makes sense? I can do whatever I want as long as I do it to both sides. So let's pretend x is vi plus vf over 2. Vi plus vf over 2 times t. Well, how do I get rid of this stuff that's inside the brackets? Divide by everything that's inside the brackets. But I have to do that to both sides. Just like I'm dividing both sides by x here, and dividing both sides by whatever's inside the brackets there. So what am I left with? It's an ugly looking equation, but it works. Now, Kessler, when you see the way that I'm going to do this, you're going to be like, oh, that was a lot of work. That's okay. Yeah, a lot of work, it's fine as long as it gives you the right answer, right? Delta D, what do we say that was? 87.5? 87.5 meters. VI was, I think it was 10. Yeah, 10. VF was 25. Okay, do this with me. Please take out your calculators and do this with me on the calculators, because this can be a little bit ugly here. Let's do the bottom first. Let's say 10 plus 25. Got it? 35. You probably could have worked that one out in your head, I'm guessing. Divide that by 2. 17.5. So I've got my denominator now. It's going to be now 87.5 divided by the answer I just got, 17.5, gives me a time of 5 seconds. There's my answer, 5 seconds. Now look at all the work I did. It's correct, but boy, it's a lot of work. Anybody have another idea for solving this? It might have been quicker, Emily? Yeah, I would have went A is equal to delta V over delta T. Now I want to get T on the top. So let's multiply both sides by T. Ends up canceling out on the right-hand side, right? Now let's divide by A. VF is 25 minus 10. The acceleration was 3. Gives me 5.0 seconds. How's that one for you, Kessler? Okay. Guys, you know what? I'm glad you said that one. I'm glad you said to use that equation, because it makes a great point. Clearly, there's a way that's more efficient than other ways, right? That's usually the way it's going to be. But you pick what lots of people would consider to be the wrong equation. It's not the wrong equation. As long as it's from the right group, you're not going to go wrong. Now, you might make a mistake of rearranging or something like that, but assuming you do all that stuff correctly, you'll still get the right answer. Okay, the worst case scenario is you do all that work and it's like, I just can't figure it out. I just can't get time. I just can't figure out how to do that. So then you got to start again. But that's the worst case scenario. You're not going to get T is equal to 17 and think you have the answer, but really have the wrong answer. It's not going to happen unless you make a mistake somewhere, right? Try to find the most efficient one, because there will usually be an efficient one. But if it doesn't work out, don't sweat it. Don't spend 20 minutes trying to find the quickest equation, right? Don't spend 20 minutes trying to save yourself 10 minutes. Does that make sense? All right. How about these two equations on page 47? I'll give you a little bit of time to work on those yourselves. Okay, let's have a look at question number 2. I know a number of you are still working on that. I have a little bit of trouble with that. Hey, listen, that's okay. Okay, we're doing these acceleration problems for the first time. If I expected you to be perfect at these right away, then I wouldn't have budgeted a few days to do acceleration. I wouldn't give you the number of problems that I'm going to give you on acceleration if I expected you to be perfect at it right away. Okay, you're going to have trouble. Okay, that's normal, completely normal. We just want to try to improve. right? So that over the next couple of days, we get pretty good at this. It's okay if you're not good at it yet. All right, so number 2 says an elk moving at a velocity of 20 kilometers per hour accelerates at 1.5 meters per second squared for 9.3 until it reaches a maximum velocity. What is the maximum velocity? And I told you, I don't care whether it's kilometers per hour, meters per second, or otherwise. What kind of a problem do we have here? Is this group A or is this a group B problem? It's group B. It involves acceleration. This elk was going at 20, and then it's clearly it's speeding up. To what speed, what velocity? We don't know, but we know that it's speeding up. It's a group B problem, which means those ones that we had squared off in blue versus the one in red, those are the ones that we're going to pick from. Let's write down our givens, and then let's see if we can find one that works for us, all right? Tell me what 20 kilometers per hour represents here. I'm going to define north as positive, by the way. What's the 20 kilometers per hour? Yep. Good, that's going to be VI, the initial velocity. As I was walking around and people were asking me questions, I think most people recognize that VI was 20. If you didn't, that's okay. If you're having trouble understanding why that's VI, just let me know and I can try to help you out with that. All right, we got another number here, 1.5 meters per second squared. What does that represent? Nicole, what's 1.5 meters per second squared? Is that V, VI, VF? Acceleration, good. Good. We got another number, 9.3 seconds. What's that one going to be, Mary? Time. Delta T. And what are we looking for here? Calculate its maximum velocity in kilometers per hour. Jordan? Good, that's VF. It's the final velocity. Now, there's a couple ways that you can deal with this. The way that I would deal with it personally is to go with A is equal to delta V over delta T. Honestly, that's the simplest equation, so when I can use that, I'll use that. There's one thing that you can learn from me here today, is take the easy way out. If you got 5 equations that you can use, and one of them is easy and 4 of them are hard, choose the easy one. So that's okay if you choose one of the harder ones, but why not? Why not take the easier path if you recognize it at least? All right, we're looking for VF here. It doesn't actually appear in this equation, but that's okay. I'm going to solve for delta V and then we'll deal with that. I'm going to solve for delta V by multiplying both sides by T. Then it disappears from the right side. It cancels. Okay? So now I've got delta V is equal to A times T. Let's get the number for that. A is 1.5. T is 9.3 seconds. What does that work out to be? 1.5 times 9.3. Yeah. 13.95. All right. There's delta V. But we also know that delta V is VF minus VI. The final minus the initial velocity. Now let's solve for VF. VI is subtracted from the right-hand side. How do I get rid of that? Add it. So it's going to say delta V plus VI equals VF minus VI plus VI. Well, negative VI plus VI disappears, right? So VF becomes equal to delta V, which I just found, 13.95, plus the initial velocity of, by the way, what was that in meters per second? That was 20 times 1,000, 20 times 1,000 divided by 3,600. And I think that worked out to be 19.4, was it? Which technically should be rounded to 2 digits. Technically should be 2 digits, although we're not going to lose any sleep over that right now. Why 2 digits? This is 2, this is 2, this is 2. Final answer should be 2. If you said 19.4, 19.5, whatever works out to be, then that would be okay too, for now, at least. All right, let's take a look at another example here then. Listen, we're going to get there. If this is hard for you right now, that's okay. It probably should be. It gets easier. 1.13 on page 48 says a cattle train traveling west at 16 meters per second is brought to rest in 8 seconds. What's the displacement of the cattle train while it's coming to a stop It says assume uniform acceleration, which just means that it's changing velocity, but it's not changing acceleration. It's a constant acceleration the whole time. You know what I think I want to do first is define west as positive. Just a little thought that came to my mind, so let's do that. Just because everything is west here, right? Is this group A or group B? Does this involve constant velocity, or does it involve acceleration? Constant velocity or acceleration, Kelly? Yeah, it's acceleration. So it's group B. So all those ones that I have circled in blue are valid here. The last 5 equations under kinematics on your data sheet are valid. Let's write down some givens and figure out which one to use. Something is 16 meters per second. What is that? That's going to be VI, yeah. That's how fast it's traveling at the beginning. I'm going to make it positive because I defined west as positive. You could have made it negative easily if you had defined west as negative. The time is 8 seconds. Is there anything else that I have if I read between the lines here? What else do I have if I read between the lines? Demi? Good. Why just say VF is equal to 0? Good. So it's brought to rest. Brought to rest. So that means it stopped at the end of the problem. I mean, that's critical to get that, right? If you miss that given, then you're going to be missing some data. You're not going to be able to solve this. We're looking for the displacement. We identified it was group B. Which of the group B equations on your data sheet look like they may fit the best? If you can't figure one out, pick any of the 5. There's one, though, that is probably more efficient than the others here. Alex, what would it be? Good. That's the one I would use as well. If you picked another one, that's fine. It'll either work for you, or at least you'll know that it won't work for you. Try again. 16 plus 0 over 2 times delta t is 8. 16 plus 0 is 0, divided by 2 is 8. 8 times 8 is 64 meters. How many significant figures should my answer be? It's kind of secondary here, right? We don't worry too much about sig figs yet, but how many should it be? How many sig figs should it be? Yeah, Grant? Sorry? 3? Nope. 2. Yeah, look back to your original data. This is 3. This is 2, routed to the least precise piece of data. So we're going to say 2 digits, 64 meters. All right. Got 2 more questions for you, please, and I'm going to ask you to work on those today. And if you can, finish them up for homework tonight.